So I want to point out I ran into Batman the other day riding his bicycle. So time must be tough. He lost his Batmobile. I thought that was funny. All right, let's go ahead and do this one. So here we have a uniform rod of mass M1, and then it's being hung at the very end of the rod, and then it has a particle M2 that is moving leftward here with some sort of speed V, and it's going to strike it at midpoint. And the question wants us to find what this N is for M1 over M2. Okay. All right. So in order to do this, you have to recognize to set up conservation energy and conservation angular momentum, only because the two concepts play well together. So I'm just going to start with KE. All right, so it says that the particle is moving at some speed here, v. It's going to strike the rod and it's going to come to a stop. So I'm visualizing all of the Ke initially in the particle is going to get transferred to the rod because it says elastically, so energy has to be conserved here. So other than that, I'm just going to set up KEI. KEI is for the particle M2, so it'd be generically 1/2 mass v square. What mass? Mass 2, because I'm looking at the particle, and v is just given as v in the diagram. And then on the right side, all that energy is going to cause the rod to rotate around some fixed pivot at the very top here of the rod. So that would just be 1/2 I omega square. This rod does not have a K linear because it is just being rotated at the end of a location here. Okay, so no one to introduce Ke linear for the rod, no one not to, because it's being fixed. It only rotates. So here 1/2 is going to cancel out on both sides because it appears on both sides. So I'm just going to go ahead and expand this and clean up a little bit. So on the left side stays the same because it's M2V square. And on the right side, I'm going to go ahead and break up the moment of inertia for this particular system, which is 1/3 M1L square. It's 1/3 because it's being pivoted at the very end. The mass 1 because the rod is indicated or denoted as M1. And the length of the whole entire rod, I'm just going to call it L. Okay, so the diagram here doesn't have L, but from top to bottom, that's just a distance of L. Okay, and then what you notice here, instead of writing omega square, I broke up omega into V over R, but R being the length of the rod here. And so therefore, omega square is simply VF square divided by L square. So once you distribute the square to the VF and L square, as it L, it becomes L square. So from there, so I'm just going to go ahead and do that for you. Okay, so make sure when you distribute this exponent, it goes to the variable on top and on the bottom. So as you can see here, the left side stays the same. The only thing different here is that the L in the parentheses now is square because I've taken care of that exponent too. But I see an L square outside in the numerator. I see an L square inside the parentheses in the denominator. So I'm going to go ahead and cancel the L square out there. And that leaves me with this statement. Now, once you get to here, I encourage you to really, focus on what the question is looking at. It's looking at M1 over M2, So right away, once I get to this fourth line here, I'm just going to go ahead and get my work to look like M1 over M2. I know it's not perfect. So M1 on the right side is already in the numerator. I have an M2 on the left side. So I'm actually going to move M2 to the right side by dividing both sides by M2. So I have M1 divided by the 1/3 here. I just went ahead and just kept the 3 because that's in the denominator times M2. Okay. It looks like it. I know there's a 3 there, but at least it's in that format where it's M1 over M2. Well, I need to do something with this VF square. Well, the VF square, I don't know what VF is, and I don't know what V initially is here for the particle. So I'm going to go ahead and get this VF square to the left side by dividing both sides by VF square. So it's in the numerator here, so I'm just going to move that term to the bottom left. So I highlighted V square over VF square here because, well, I don't know what these quantities are. I need to keep M1 and M2 though, because that's what the question essentially is referencing, right? So at this point in your work, you have to, decide what to keep and what to get rid of. Well, I need M1 over M2, so I'm going to keep that. I don't know what V square is. I don't know what VF square is, so I'm going to get rid of that. So as you practice, know what to keep, know what to get rid of. Well, how do I get rid of V square over VF square? Well, I'm kind of stuck here, right? So this type of problem is designed so that you have to use a couple of different concepts in physics to crack it out. All right, so I've already done what I can with kinetic energy, conservation kinetic energy here. The only other thing I can possibly set up is conservation angular momentum. So here, I'm just going to make the statement, the initial angular momentum of the system must equal to the final angular momentum of the system. Well, initially, I have a point mass that's moving, and it's going to strike at midpoint here of the rod. Okay, so I can convert linear momentum into angular momentum simply by multiplying the moment of the arm relative to the pivot that's perpendicular to where it strikes it. So I'm just going to expand my work. So generically, C for a point mass, this is the coefficient of moment of inertia. So we treat the particle as a point mass, so which is be CMR squared. So here, C is just 1, because it is a point mass. M is M2 because I'm looking at the particle. V here, that's because the diagram says that the initial speed for the particle is just going left with some speed V. And you notice here in the parentheses, though, I highlighted L over 2. That's because you need the distance from where it strikes the rod. Well, it strikes it in the midpoint, and if I go all the way up to where it's pivoted, that is the distance of L over 2. So here's what I have for you. So I measured it for you there. Okay, L over 2. So that's why this particular distance is L over 2, and these two vectors are already perpendicular to each other, so I'm done there. On the right side, I just broke up LF into IF omega F. Well, that's because initially the angular momentum is contributed by the particle, but afterwards it came to a stop, so the only thing now moving is the rod swinging on its end. So I'm simply going to say angular momentum in the final frame, which is IF times omega F. Okay, so here I'm just going to go ahead and leave out the C because the C is just a 1 for this particular problem because it is a point mass. I'm going to break up IF. IF once again is just 1/3 ml squared, m of the mass, or m of the rod here, and the length of the rod. And likewise, like over here where I broke up omega into VF over L, I'm going to do the same here. So omega is just VF over L. And then from here, I'm just going to clean up a little bit, okay? So here, you notice that there's an L there, and then there's an L on the bottom. So if you move this L from the top left to the bottom right, that will become L squared because L times L is L squared, and that's going to cancel out with this L squared on top. Okay, so hopefully your math, your algebra skill is good here that you're keeping up. All right, so once I do that, I'm just going to go ahead and clean up a little more. So the only thing left on the left side here is M2 times V divided by 2. And then the only thing left on the right side is literally just 1 times M1, which is just M1 times VF, and divide that by 3. Okay, so if you want, you can keep this as 1/3 like I did, or you can just put the whole entire thing over 3 like I did on the left side. It doesn't really matter. What's more important here is that you need to get rid of V squared over VF squared on the left side. So therefore, I'm going to use the same trick here. I'm just going to go ahead and get M1 and M2 on the same side, and then V and VF on the same side. So M2 is on the top left. I want to divide both sides by M2, which will cause it to go to the bottom right. And then this VF here is in the top right. So I'm just going to go ahead and move it down to the bottom left by dividing both sides by VF. So it's going to look like this, okay? And then this 2 here, I just moved it up there. So once again, the goal is to just get V and VF on the same side, because on the left side, you need to get rid of it. But I do want to point out that you have to look at this carefully. On the left side, when you set up conservation kinetic energy, the V is V squared, the VF is also squared. But when you set up conservation of angular momentum, you notice here this is just V and this is VF by itself. They're not squared. But that's easy to do. Well, how do we get the right side V's to look like the left side V's? Just square both top and bottom. But make sure you do it to both sides of the equal sign. So I'm just going to go ahead and do that. So V on the top is now going to get square. VF on the bottom is going to get square. And on the right side, I have to square everything too. So 2 square is 4. M1 square is just M1 square. And then 3 square is 9. And then M2 square is just M2 square. So now I have 2 statements that are equal to each other. So I have a V square over VF square equals M1 divided by 3M2. But likewise, I have that same statement. However, it's equal to 4M1 square divided by 9M2 square. So I'm just going to set these 2 functions equal to each other. So my cursor here that I'm circling, M1 divided by 3M2 is on the left side. Well, all that equals the same statement, so I can set them equal. So that would be equal to 4M1 square divided by 9M2 square. So as you can see here, I can start canceling stuff out. There's an M1 on the left side, but on the right side, there's M1 squared, which would imply that it's M1 times M1. So I'm just going to cancel out the exponent 2. And likewise on the bottom, I have an M2. I'm going to cross that out. I'm going to cross out the square term for M2. So as you can see here, now we have just M1 over M2, almost, right? So to get M1 divided by M2 by itself, I want to move the 9 up to the top left, and I want to divide both sides by 4, or I can just move this 4 to the bottom left. So 9 got crisscrossed upward, 4 got moved down. So it looks like this. So if you want, you can reduce at this point. 9 divided by 3 is just 3. So really, this is just 3 over 4. So the left function here, the left fraction, not function. So it'd be 9 over 12, which is the same thing as 3 over 4. So I know, though, that m1 divided by m2 is up here, right? The initial statement tells us that m1 divided by m2 is equal to n over 8. So wherever m1 divided by m2 is, I can make this true statement substitution. So instead of saying m1 divided by m2, I can just replace m1 divided by m2 with n over 8 because that's what was given to us. It's saying that the ratio between m1 over m2 is some value n divided by 8. So I'm just going to substitute it out. Like I said earlier, the left side of the equal sign, 9 over 12, is just 3/4. So as you can see, the only thing now we have left is just n is what ultimately we're trying to find. So I'm just going to crisscross and multiply both sides by 8. So 8 times 3 is 24, and then divide that by 4. So n which is equal to 6. Okay, so that is your answer for this particular problem. I hope that helps. If you need to, listen to again and keep up with the algebra stuff. All right, good luck. Stay nerdy.